Hi everybody, if you're logging on YouTube, so this is April 14th and it's our last day where we're going to be talking about exponential functions. So I'm going to go through one more example here. The questions that have been coming in, a lot of people are curious about these more modeling focused questions where you're not explicitly asked to solve a particular exponential or logarithmic equation, but you have a scenario, right, that you have to interpret. And so this is a question from our web work homework. I think this is number 18. And so we're going to go through is we'll walk through this example and sort of look at the different pieces. So the scenario is this: you have some population of rats. That's what the problem stated. So you have a rat population, and it's growing with this function. So at a particular time t, we can use this formula to figure out how many rats there are. Okay, so it's 62 times e raised to the 0.04 t. So this would be a typical exponential function, right? So you'd have a times b to the t. So it looks something like this. And when we're measuring t, the important thing to note is that we're saying this is years since 1994. So when t is 10, that would be 10 years after 1994 or 2004. When t is 5, it would be 1999. And then n of t is measured in millions. So the two web work problems were these first two bullet points. What were the rat populations in different years? And then I threw in this other one where we can then solve an exponential equation. Okay, so what we'll do, all right, so here's our problem. And so we'll walk through this one. Okay, so to start out here, let's start here in red. All right, what's the rat population in 1994? Well, in 1994, you have to think about how many years since 1994 is 1994. The answer to that is 0, right? So what we'd be saying is this is our initial population. So how many in year 0, how many rats were there? What was the rat population when all of this started, when we started modeling, which is n of 0. And so you would get, this is 62 times e to the 0.04 times 0. And one thing to note here is that this, right, when I plug in 0 here, I'm going to get e to the 0 power, which just ends up being 1. And so the answer to this is 62, right? So if we went through the full computation, we could see that the initial population is 62 million. But also in the exponential function, right, this value a, we know gives us our initial value. So we could have just read it off from there, right? So the next part we'll do in blue, right? So in blue, this one would be a little bit different. Okay, so what is the population in 2007? We have to think about, hey, what's our input? And so years since 1994, how many years do you need to pass to get to 2007? And the answer is 13. Right, so what we would do is we would look at this value n of 13, which is 62 times e to the 0.04 times 13. Okay, now for me, this isn't something that I can do in my head. So what we would do is we would just go over to Desmos and we could evaluate this. And what we're going to find is that the answer to this is, let's see here. That's about 104.29, right? So it's approximately equal to this. So after 13 years, you had about 104 million rats, right? This would be the interpretation to this problem, okay? But when we introduced logarithms, there was this whole other side of it, right? So we weren't just plugging in numbers. To use logarithms, we were actually able to make predictions or ask questions using this model, right? So if you're modeling rats with this equation, we could ask the question like when, right? When will the population reach 200 million rats, right? So we don't know. Maybe it's the year 2007, and we're trying to predict the future, right? So based on all the data that we have at our disposal, we are modeling what's going on, and we're trying to make a prediction and saying, hey, when will this population reach 200 million? Okay, so what we would do is we'd set up an equation and we would say, I want to know when my equation 62e to the 0.04t, when is that equal to 200? Okay, so remember the units on our output are millions. And so we get an equation that looks something like this, right? So 200, we want to know when will this, at what year, right? What's the input going to be to give me an output of 200? Okay, so we go through, and what we'll do is solve this for t. Okay, so if we remember our process here, we're going to try to get that exponential term by itself, and then we're going to use a logarithm. So I'm going to divide both sides of this by 62. And so I get e to the, let's keep it in green. So we get e to the 0.04t is equal to 200 over 62. I'm going to take the natural log of both sides of this thing. Okay, so I'm going to end up taking the natural log of both sides. And so remember, natural log is base e, so e and natural log undo each other. They're inverse functions, so we're left with 0.04t is equal to the natural log of 200 over 62. And then we divide by 0.04. So this t, the years, would be this natural log of 200 over 62 divided by 0.04. Okay, now keep in mind, this may not be the most useful number, but this is the exact answer, right? So the very precise answer that we would get is this natural log of 200 over 62. And then we could go back, use the calculator, and then interpret our data, right? So this is going to give us the most precise timing, so we can have absolute precision, and then we can go back and relax that precision as needed. Okay, so I'm going to go over to Desmos here, where I have our function modeled, right? And so I put in our function here, n of t, and then just a second ago I asked, what was the population after year 13? And so now the question was, when does it reach 200 million? Well, we had this computation, right? So we wanted to know what this number was. Turns out it's 29.28, right? So it's approximately this. And if we look at this on the graph, right, so we should see that somewhere over here, when we're at 29, we should be hitting 200 million, right? So this point on our graph over here, right around, 29, a little more than 29, we're hitting 200 million. Okay, so this would be our exact answer. And then if we wanted to, right, so we could use Desmos as a tool. We could just graph the line y equals 200. It would give us a nice intersection point there, and you can see that this would be our approximate answer, right? So after 29.28 years, we would reach 200 million brats, or more precisely, this number of years, right? So this would be our absolute precision. Okay, so putting that into context, 29 years after 1994 would be 2023, right? So if we were making a prediction here, if it was today and we were using this model, we would say we would make a prediction that in the year 2023, we would have 29 or 200 million rats, right? Which is 29 years after 1994. Okay, and so as we've seen, this type of question is very important and very hot topic right now, right? So when you have some sort of exponential growth, trying to get this model right, and then using it to answer questions like this, when will we reach certain populations, is important for lots of people. Okay, so I'll kick it over to Jordan, Nick, if you have any questions here.
No, that makes sense.
Makes sense?
I've been able to figure it out for the most part.
Okay. All right, so what we'll do is we will, so we'll stop our exponential functions and logarithms here. But as always, if there's more questions, send them to me via email or anything else. Any other way you can get in contact with me. All right, so what we're going to do is we're going to jump over to our next chapter, right? So if you go onto our Plato page under activities, we're still using this guided activities for pre-calculus. And so what we're going to do is we're going to go over into chapter 7. Okay, so chapter 7 is all about triangle trigonometry. Okay, so so this is going to be, we're going to start going back into trigonometry, which we did before, and specifically we're going to introduce this idea of triangles. Okay, so one of the big things that's going to come out of this triangle trigonometry is how can we do a lot of these geometric calculations. So if we are sort of measuring things physically in our space, if we can break it up into triangles, how can we, compute the different side lengths using trigonometry? So this is very important in geometry. And then one of the big applications that we're going to see later on is how we can use this triangle trigonometry to understand rotations. And so rotations, in particular, like on a computer screen, what's the mathematics that's going on behind that allow things to move and allow things to rotate? So if we go back to our Plato page, I opened up our week April 13th to 17th, and I put in our last Desmos project, which is going to be about motion. Okay, so something on your screen is going to have to move. So I wanted to show you sort of what that means. Okay, so you'll create a graph, and then there's going to be some sort of slider that is on a play button that will be going back and forth. And then what you're able to do is then see the graph move. Okay, so what's happening here in this picture is there's a point down here on the shoulder, so on Olaf's shoulder, and all of these pieces are rotating around this point, right? So you can imagine there's a fixed point right here, and it's just sort of rotating back and forth, right? So with this rotation, what's happening on the screen is, to us, it looks like an animation, right? So if you're thinking about things like CGI or digital animation, or how do they make cartoons and things like this, right? So anything that's going to have this digital animation, we can understand, we can use the mathematics in the background. And so Desmos is a particularly nice tool for this, because over here in the left sidebar, right, you are actually able to see the equations that are going on behind the scenes, right? So you can open it up and see the mathematics, but over here on the right-hand side, you get this picture, right? So you're actually, this would be like, in some sense, computer coding, right? So you're writing the code over here, the mathematics, and then the images are appearing over here, right? So this is a way that you can actually create an animation. So this is one example that a student created in a past semester. Okay, and so some more examples there. There's 4 examples here. So you can see that there's some motion aspect that's happening here, right? So this student created a fox, and then the tail is moving up and down, right? And so what the way that this is happening is somewhere in this list of things, right? So we have this slider that's moving back and forth, right? And so then the tail moves up and down, right? So up and down. So we're going to see what we're going to do through triangle trigonometry at the end of chapter 7 is we're going to develop these equations right here. We're going to figure out, hey, what is going on with all these equations with sines and cosines and trigonometry to get these things to rotate back and forth, up and down, right? And so I'll open one more, right? And so you can see again an example where we have a picture, and then we have this motion that's happening. It looks like the turtle is swimming. So as we're going along here, if you want to start working on your Desmos projects, you don't have to get them to rotate just yet. Oftentimes it's very helpful just to have your static picture, right? So draw your picture that you want to draw, and then we'll identify a piece of it that we want to rotate. But if you already have it done, if you have it drawn in with the line segments, that's going to make it a lot easier then to get them to rotate, because I'll show you how to do very specific substitutions, and then we can get things to move. Okay, so we're going to go ahead and shut these down. But go ahead and check these out, get some ideas, and it would be a good idea to start looking at your project and see what we can do. So this will be the due date for this isn't until the end of the semester. So we have three weeks, including this week, before we will be wrapping things up. Okay. So for me personally, this is sort of one of my favorite chapters, just because it puts a lot of the ideas together that we've been working on, and then we get to really do this cool thing where we get to create some animation, right? So we get to come out of this with hopefully something that you're particularly proud of, that was challenging to create, and you can show off like, hey, look, I went into pre-calculus, and now coming out of that, I can actually create these digital animations using mathematics. So that's sort of the goal here. All right, and so as I alluded to, the mathematics behind this is all triangle trigonometry. So whatever that means, we're going to see how we can use trigonometry to figure out different side lengths of triangles, and then prove some different identities about how things rotate. Okay. So if you want, here's sort of our learning goals for this section. But all right, so if you're playing along at home, one of the things that you can do, so in this document, you'll notice that the links here are highlighted, right? So if you want to, you can bring up this unit circle graph, and Desmos, just by clicking on this link, so anything in these blue boxes right here, you can click, and then it will give us some instructions. Okay, so if you remember, we have this graph that we looked at a little while ago in class. I think we actually looked at this one before we left for spring break. So give you all a moment. You can give me a thumbs up or something when you have this open and we're ready to talk about it. Good. So far, so good. Okay, so I don't know what the best way to dual screen this is. We want to go back to we want to keep going back to our notes here as well. And so I guess I'll just sort of flip back and forth between this and our notes. Okay, so all right, so what we're going to do is, it says here, right, so we're going to click on the folder next to the triangle to make the green triangle appear. It looks like that's already there. And so when we talk about triangle trigonometry, right, these are sort of the triangles that we're going to be talking about. Right, so anytime I have a point on my unit circle, what I can do is I can use that point and then the origin 0, 0 to create a triangle, right? So I'm gonna use this distance right here to give me the base of my triangle. This will be the height, right? So it's gonna be a right triangle, and then I'm just gonna connect the point on the unit circle to the origin, right? So you get triangles that look something like this. Okay. All right, so question 1, use the radius slider to change the radius of the circle. How can you use the coordinates of the unit circle to determine the lengths of the sides? Okay, so what we're going to do is we're going to use this radius slider to change the length of the circle. Okay, so we're going to change the radius, and at any point in time, right? So as I change this, what I want to know is what are the lengths, right? So there's 3 sides to this triangle. What's the height of the triangle? What's the length of the base? And then what's the hypotenuse of the triangle, right? So we're going to go ahead and change these and see if we can figure out, if I have this triangle right here, how tall is it, how wide is it, and what's the length of the hypotenuse. So anybody have any ideas? you know, how we might be able to figure that out. Right, so this is going to apply to basically to all these triangles, right? So any single one of these, I should be able to figure out, you know, what's the height, what's the base, and then what's the hypotenuse.
Well, the x-coordinate will give you how far how long the bottom side is, right?
Okay, so this x-coordinate right here, so you're saying this 1.732, that the length of this base should be 1.732.
Mm-hmm.
Okay, so down here, this should be 1.732, okay. And then that came from this 1.732 here.
Mm-hmm.
All right, and so what else do you see?
So then the y-coordinate's going to be the height.
Yeah, so this is going to be 1, right? And now what's the hypotenuse going to be? So if this is 1 and 1.732, what's the hypotenuse? Do we know how to compute that?
Pythagorean theorem.
Wouldn't you multiply the square that's at 1.732 and then find the square root of that to find what the hypotenuse is?
Close, right? So you could use the Pythagorean theorem, right? So you would end up squaring it, right? So you'd get x squared plus. So let's go ahead and do it that way, right? So Pythagorean theorem says you could do a squared plus b squared equals c squared, right? So you'd have a squared plus b squared equals c squared. And so if this was a, b, and c. Okay, so this would be one way, right? So you could square them. So as you said, Jordan, right, you'd square 1.732. You would then add 1 and then take the square root. So one step in there off. But right, so you would plug in these here. So that's a lot of work. You don't actually have to do that. So if you did that, you would get the right answer. That's one path forward, but that's a lot of work. There's an easier way. Any ideas on how to do it in an easier way?
I don't know.
So do you see this orange circle that I'm putting out over here? R equals 2. What is that?
That's the hypotenuse.
Yeah, that's the radius of the circle, right?
Mm-hmm.
And that's also the hypotenuse, right? So the radius says what's the distance, right? So the distance from here to any point on the circle, right? So the distance from 0, 0 to any point on the circle should be the radius, right? So this right here should be 2, okay? And so as I think about this, right, so the radius, that R value, right, is going to be the radius of my circle. That's the hypotenuse of these triangles that we're thinking about. And then this X coordinate is going to be the length of my base, and the Y coordinate is going to be my height, okay? Yeah, so from this, just from this diagram, if I pick a point on the unit circle, I'm able to actually determine, you know, I'm able to determine the dimensions of these. And so what we see now is we have this triangle and we're making this connection to the unit circle, right? So, hey, this right triangle, it seems like if I had any right triangle, I would probably be able to fit it into a unit circle, which now I'm starting to make these connections. And if we remember when we brought in the unit circle, we started to think about sine and cosine based on this unit circle. So we can now connect these two ideas. Somehow we have this triangle, we have the unit circle, and then we have these functions, sine and cosine. Okay. All right. So, whoops. Let's get back here. Okay. So we talked about this. How can we determine the length of the size? And we determine how the size of the triangle changes as you change the radius. Okay. And so here's an example. How much bigger does the triangle get if this circle has radius 3 compared to radius 1? Okay, so let's go back here and let's go down to radius 1 and let's sort of check our values. So this is 0.866 and 0.5. And if I go out to 2, when I go out to 2, right, what happened to these numbers right here? So it was 0.866 comma 0.5. And now when I went out to 2, what happened to these numbers?
They doubled.
They doubled, right? And so if I go out to 3, what do you think is going to happen to them?
They might triple.
Yeah, so let's go ahead and let's check that, right? So we'll take this slider all the way to 3. We see that, hey, at least 0.5 tripled. That gives us 1.5. And then if we want to here, we could go and check this point. What is 0.866 times 3? Oh, and that is the 2.598. Right, so that number also tripled here. Yeah, so it seems like all my coordinates are going to be multiplied by that radius, right? So at least in this, our initial exploration here, now if I could try, I could go out to 4, like I could put this out to 4. It seems like, yeah, that seems reasonable, right? That these numbers all got multiplied by 4. And so if those are our side lengths, right, that radius, I'm just going to multiply those side lengths by our radius. Okay, so I think we're making some connections now. But the one thing for me that's missing is this idea of, you know, we were talking about the unit circle, so we were talking about sine and cosine. So if I gave you this triangle, something like this with this angle theta, I would want to figure out, I would want to be able to use sine and cosine to determine the lengths of the sides of this triangle. So let's go back over here and let's mark this up a little bit. So what we're going to say is that this would be r and this angle would be theta. Okay. So if this angle is theta, do we remember how to find these coordinates, right? Like, so what is the x coordinate on our unit circle, right? So if I walk along a distance of theta, or in radians, right, so that would give us our angle measure. Do you remember which trigonometric function gave us our x coordinate and which one gave us our y coordinate? Right, so we're thinking about sine and cosine. One of them gave us our x, and one gave us our y. You remember which is which?
Cosine is x, right?
That's right. Yeah. So this is always going to be cosine of our angle theta, and then this too is going to be sine of our angle theta. Okay. But that's not really true, right? So it's close, but it's only true when r is equal to 1, right? So when r is equal to 1, then cosine of theta and sine of theta, we would get these nice values. But if I come out here where we were, right? So we were out here at 4. And so this isn't going to be cosine of theta anymore, right? This is going to be, I'm going to have to multiply everything by 4, right? So if my radius goes out to 4, then I'm going to have to multiply all those numbers by 4 or 3 or 2 or whatever my radius is. And so we're going to see that these numbers for radius r are going to be given by r times cosine and r times sine. And so if I put these down in the triangle, if the radius is r, then this down here will be r cosine of theta. And then this over here, this will be r times sine of theta. Okay, so for any triangle, I'm able to compute the side lengths. If I have the hypotenuse, I can go through and compute what the base should be and what the height of that should be just based on one of the angles. Okay, so as long as this is a right triangle, I'm able to figure out, you know, what the side lengths are based on one of them. And so this is a really powerful tool because just with a few little bits of information, right, one angle and one side, I can figure out the other two side lengths, and presumably I could figure out this other angle too along the way. Right, so really a nice tool for us to have. Okay, so let's check out our notes here. All right, so so far so good. So we used our knowledge of sine and cosine to determine the lengths, right? So we said that this length over here was r sine theta, and then the length of the base was r cosine theta. Okay. So Jordan, Jody, Nick, do you all remember this word SOHCAHTOA? Have you heard that before? Yeah, that one's pretty good.
Yes.
Yeah. So as I teach this, a lot of students are familiar with that, SOHCAHTOA. So what we're going to do is we're going to give names. If we have a particular angle here, theta, right? So theta is going to be this angle down here in the bottom left. It could be depending on what we want to match up with. But this is our, right? These are our names that we're going to be giving to things. Okay, so so if you pick your angle theta here, the opposite side means we go across the triangle to the opposite side, right? It's not touching this angle theta, right? So remember, we always have a right triangle, and then the opposite side is going to be the one across the triangle to the opposite side, and the adjacent one is going to be next to it, right? So it's going to be right and down next to it. Okay, so if we flipped our triangle around, right, so we could have a right triangle, and then we could put theta up here. This will always be our hypotenuse. It's across from the right angle. But if I'm talking about this angle theta, my opposite side is now down here on the bottom. Okay, so one of the things that we want to always be thinking about is what angle are we referring to? So depending on what angle we're talking about, if it's down here on the bottom left, the opposite side will be across, and then the opposite side is still across from the angle, right? So if you're talking about this angle up here on the top, the opposite side is down on the bottom, and then the adjacent side would be off to the right. Hypotenuse never changes. It's always across from the 90-degree angle. Okay, so what we're going to do is we're going to build up this idea and try to understand SOHCAHTOA. Okay, so what is SOHCAHTOA? Where does it come from? And you know, how can we use it? Okay. So I'm going to kick it over to you really quickly here. So it says using the fact that tangent of theta is sine of theta over cosine of theta, can we represent tangent of theta as the ratio of sides of the triangle? Okay. Well, we missed a question here, right? Use two triangles on this page to represent sine of theta and cosine theta as the ratio of the sides of a right triangle. So any ideas?
So for sine of theta, would it be O over H, opposite over hypotenuse?
It is, and do you want to talk through sort of how we got that? So what I'm going to do is I'm going to bring up a whiteboard so I can have a little bit better writing capabilities here. But I'm putting up our two triangles that we've been thinking about. Okay, so if we have our two right triangles, what we have is we have that the right. So the sides are r cosine theta is along the bottom, r sine theta is along the right. So your claim, Jordan, is that sine of theta is equal to, you said, opposite over hypotenuse?
Yeah.
Okay, so let's see if we can go ahead and verify this identity. Okay, so what I'm going to do is I'm going to go ahead and I'm going to take this opposite side, right? So opposite, I'm going to put in red, is this side over here, and the hypotenuse is this side of the triangle, which is over here in blue. Okay, so to bring it back over to this triangle, the hypotenuse of my triangle is going to be r, and then the opposite side is going to be r sine theta, right? So if I take this, if I do O, and then I divide by h, what I should get here is this should be equal to, in red, r sine theta, and then I'm going to divide all that by r, which is my hypotenuse, and well, it looks like these r's are going to cancel, and then what I'm left with is sine of theta. Right, so if I put these sort of this language together, if I put together my r sine theta, r cosine theta, r, right, so this stuff over here on the left, I put it together with this new language, opposite, adjacent, hypotenuse, we do get this nice identity right here. Okay, so we get this sine of theta is always the opposite over hypotenuse. Okay, so I'm going to give you all a minute. Try to do this with cosine of theta. Right? How would you get cosine of theta? So, right, so if we're thinking about it, we would take our adjacent side, right, which is our green, again, and if I divide by my hypotenuse, what we would get is we get this r cosine of theta. We're going to divide the whole thing by our hypotenuse, which is r, right? So again, these cancel, and what we're left with is cosine of theta. Okay, so we get another nice identity here. Cosine of theta is always the adjacent side divided by the hypotenuse. Okay, so this is where we get so far, right? So when you see this, these words, right? So this weird word SOHCAHTOA, this is what we're saying. Okay, so we're saying that the sine, right? The sine is the opposite of our hypotenuse. Okay, so the S here stands for sine, is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then for the last one here, when we do TOA, right? So what do we think? Tangent should be then, what do we think about tangent? Right? Opposite over adjacent. Right, so we should see that tan theta is the opposite over adjacent. So let's use our colors again, right, to see if this is actually true. So our opposite side was in red, which is r sine theta. And then our adjacent side is in green, which is r cosine theta, right? These r's are going to end up canceling out. And so no matter what that hypotenuse is, my tangent of theta is always going to be equal, right, to this, right? Opposite over adjacent, which is sine theta over cosine of theta. Okay. And so I should have put an extra step in here. Right? So we should have said this was the adjacent side divided by the opposite side. And so that's all tan theta. Okay. And so this is a way that we can sort of verify that all of this is going on. Now, notice that we didn't use any numbers here, right? There was nothing in this that had any numbers whatsoever. So this is always true, right? So no matter what our triangle is, if the hypotenuse is r, then this side is going to be r sine theta, this side is going to be r cosine theta. And then we have this nice relationship that we have sine is the ratio of the opposite side of the hypotenuse, cosine is the ratio of the adjacent side to the hypotenuse, and tangent is the ratio of the opposite side to the adjacent side. Right? So if I divide pairs of side lengths, then it gives me what the tangent of the angle is, the sine of the angle, or the cosine of the angle. Right? So this whole idea, something that you've probably seen in the past, right? This idea of SOHCAHTOA is now sort of explained all in this picture right here. So I'm always curious, right? So most students have seen this before, but was it ever just sort of presented to you as, here's a fact, right? This thing is true, versus the way that I presented it here was, here's why, right? So we should see the reasoning behind this, right? Why are these things true? How can we build them up through our understanding of the unit circle and our understanding of, building this particular triangle inside of those circles? So my question here is, have you seen this sort of treatment before, or when you saw SOHCAHTOA in the past, was it just sort of presented to you as a fact?
Just a fact.
Just a fact.
Yeah, I was like, yeah, so that's sort of one of the different things that I try to bring here. So again, what we're seeing, a theme that we'll see throughout the class is, technology is really available, right? So we use Desmos all the time. Desmos can solve equations for us very quickly, right? So we saw with the exponential equations, we can get, we can get these numbers, these answers very, very quickly. But it's more important for us now that we have access to the technology, quick computations are de-emphasized, and the understanding of how these things are working and how do we use them for bigger things is now more important. Okay. All right, so let's go ahead and jump back over here. Okay. So our familiar mnemonic device, this is SOHCAHTOA, what we just talked about. And so now we have three other, right? So we have three other functions, secant, cosecant, and cotangent, to go ahead and see if we can figure out what their relationships are. So let's go ahead and I'm going to write on the blackboard. I think that's just better than writing there on the screen. Okay, so in order to figure out these ones, secant, cosecant, and cotangent, what we need to remember is the definitions of these things. So secant theta, cosecant theta, and then cotangent of theta. Remember that these things are all, we can think about them in terms of sine and cosine. So secant theta, this is 1 over cosine of theta. Cosecant of theta is 1 over sine of theta. And then this is cosine of theta over sine theta. right? So we can, this is sort of the definitions of these that we've seen before. All right, so if we combine this with right, SOHCAHTOA, we'll keep this in the back of our mind. If I think about secant of theta, right, so secant of theta is 1 over cosine of theta, and going up, cosine is adjacent over hypotenuse, right? So this is 1 over this adjacent over hypotenuse. And so what I can do is, in the denominator, dividing is the same as multiplying by the reciprocal. So we can take the reciprocal of this, and we see that a secant of theta is going to be hypotenuse over our adjacent side, right? So if we want to write these out. Right, so we get this new relationship for secant, and then what we can do is we can do something very similar, right, for cosecant and cotangent. Okay, so I'm going to give you all a minute here to think through this before I write it down. Right, so see if you can come up with these relationships. Right, what we should have in the end.
So would it be opposite over or hypotenuse over opposite, and then adjective over, or not adjective, sorry, adjacent over opposite for the?
That's right. Yeah. Right. So you'd have this hypotenuse over opposite, right? So you'd flip this just like we did, and then for cotangent of theta, you'd have adjacent over hypotenuse times divided by opposite over hypotenuse. So what you get here is A over H times H over O. So this last one's a little bit tricky, but Jordan, you said it exactly right. It's going to be, right, this will be the adjacent side over the opposite side. Right, so we have all these relationships and we can break them out. We have all 6 trig functions in terms of ratios of sides of triangles. So now that we did this, right, we saw that, we put this together pretty quickly, right? So for me personally, I don't have these memorized. So SOHCAHTOA is something that's sort of burned into the back of my mind. But these right here, at any time that I would need these, I would just quickly effectively just write down this equation and really quickly and just see if I needed it. So I wouldn't spend any time trying to, put these into your memory, but, I think these are quick enough that on the spot, we could just go through and compute them if we needed to. Okay. All right, so what are the types of questions, right? So probably from your perspective is, this is great and all, but now I'm going to have to answer some questions about these things. So what do those kind of questions look like, and how could we answer them? Right. So one of the typical web work questions is going to be something like this, or a variant on this. So we would have our triangle here, right? So we have a triangle with some side lengths. So you're given an angle theta, and then you have 2 side lengths, 10 and 24. And what we want to do is figure out, hey, what is the hypotenuse of this triangle? And then can we figure out, I don't know what theta is. Right? So in this example, I don't know what theta is, but I can still, without even knowing what theta is, I can still tell you what sine of theta, cosine of theta, tangent theta, all those, I can measure those without knowing what that is. Okay, so I copied our problem down, and we'll jump back over here to the blackboard. Okay, so we have our triangle, and we want to know step one, what is the hypotenuse, right? So what goes up here? And then I want to know, hey, what is sine, cosine, tangent, secant, cosecant, and cotangent of all of these things? Okay, so step one, as a lot of you alluded to earlier, we could use the Pythagorean theorem, right? We could use the Pythagorean theorem to figure out this value here. So, right, so if I call this h, what we would get is the Pythagorean theorem tells us that 10 squared plus 24 squared is equal to h squared. Okay, so if I square the two side lengths, then I would get this here. So let's see, 10 squared, that is 100. And then 24 squared, right? So we could use calculator for this. We could think about this. So as a brief aside, if you want to know sort of how I would square 24, right? If I'm going to do this in my mind, I'm going to do it sort of like a distributive thing. I'm going to think about it like this. So I'm giving you sort of an insight into my mental framework, what's going on here. So I'm breaking it down just like this, and you can think about it really quickly as an area model, right? So we've done this in class a few times, right? So I'm multiplying 20 by 4, right? I'm going to multiply 20 and 4, right? So if I can multiply all these very quickly, right? So this would be 400. This is 80, this is 80, and this is 16. And so I'm going to add all these up. So I would get 400, 480, 560, and then 576. Right, so I would add all these up. It's h squared. Right, so some quick mental math if that's the thing that you're into. And then I need to take the square root of such a thing. Okay, so what is the square root of 676? Okay, so we can sort of get rid of this. So what is the square root of 676? So h is the square root of 676. And we could plug that quickly into a calculator, and what we're going to see is the answer to that is 26. Okay. So the reason that I could do that square root so quickly is there's a special triangle that's really underneath this. So you may have in your mind this idea of a 5, 12, 13 special triangle, right? So this is a Pythagorean triple, we call it, 5, 12, 13, because 5 squared plus 12 squared is 13 squared. And so what I did is all these numbers are just multiplied by 2, right? So it's a scaled up version of that. Okay. All right. So what we have, right, is this nice, right, this nice picture here. Okay. So how can I use this to? And so we'll put this over here. How can I use this to figure out the ratios of all the different side lengths? And we can do this pretty quickly. So sine, right? So we'd have sine of theta is our opposite over hypotenuse. So this would be 24 over 26. Right? Cosine of theta is our adjacent over hypotenuse. So this is 10 over 26. And tangent of theta is our opposite over adjacent, so this is 24 over 10. Okay, so what I'm doing is going through and just taking that SOHCAHTOA down the line, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And what I like to do is set up my grid in such a way that, should be secant theta and cotangent of theta. So if I set it up this way, I know I have this relationship that cosecant is 1 over sine. And so this should just be the reciprocal, right? So 26 over 24. Secant is a reciprocal of cosine, so this is 26 over 10. And cotangent is a reciprocal of tangent, so this is 10 over 24. Right, so we could go through and then figure out, hey, what are the values of all sine theta, cosine theta, and so on, right? So once I have those 3 side lengths, we're able to compute these values. Right, so this is a very typical web work type problem that you'll see, figuring out the different values of the trig functions based on a triangle. Okay. All right, so let's go see some other typical problems. So we jump back over here. So this is these are 2 other typical problems. Let's give you a chance to read them. Okay, so what we're going to try to do is we're going to try to go through and figure out, and sometimes people call it solving a triangle. So if you're given some pieces of information, right, so right here I'm given the fact that I have a right triangle, I have a 30-degree angle, and one of the side lengths is 8. Can I go ahead and figure out what the other pieces of information are? Okay, so we're going to use trigonometry, we're going to use Pythagorean theorem, and we're going to try to figure out all the missing pieces of information here. Okay. And so here's our triangle, and what we have, right? So we have some missing pieces of information. We're missing an angle that should go over here. We're missing a side length that should go over here. And we're missing another side length that should go over here, right? So what we're going to do is try to figure out, use our knowledge here to get all these other pieces of information. Okay, so what do you all think? What would be the fastest one to do here?
Couldn't you, if I remember correctly, triangles are always at 180 degrees. So if you could just add the 30 degree and the 90 degree, you'd get yourself at 60 degrees for that little green circle.
Yeah, right. So this is a big idea. So triangles have 180 degree sum. So if I want this green angle, I don't know what it is, right? So if we call this green angle theta, right? So we would have theta plus 30 degrees plus 90 degrees is equal to 180 degrees, right? So what we're given here, we want to solve this thing for theta. So theta, as you said, Jordan, plus 120 is equal to 180. So you'd have to ask yourself, hey, what do I have to add to 120 to get to 180? And so what we get is that theta in this instance has to be equal to 60 degrees. Okay, so over here, I agree. I think this would be the first place to start, right? So we're able to figure out what that angle is, because the angle sum of the triangle is always 180, right? So this is 30, 60, 90. Okay, now we can't actually use Pythagorean theorem anymore, right? So we can't do that because we only have 2 sides. Or we only have 1 side, sorry, we don't have 2. So what we're going to do is we're going to actually use trigonometry now to allow us to determine the other side length. So let's go ahead and start. We can do hypotenuse. So I can pick any of these angles, but what we're going to see is I have this side 8, and I have this red side, right? So there are two sides of my triangle if I want to figure out red. And I can pick one of these two angles. So depending on the angle that we pick, we'd be able to determine what our red side is, right? So if I picked 30 degrees, so 30 degrees, if I pick this angle right here, the sides that I'm dealing with in relation to 30 are the opposite and the hypotenuse. Okay, so if I pick 30, I have 8, right? I'm dealing with my opposite and my hypotenuse, which in this case, you know, we'll call this red H up here. So my opposite side is 8, and my hypotenuse is H. We don't know what that is. Okay, so which trigonometric function uses the opposite and the hypotenuse, right? So if we think about this backwards, in SOHCAHTOA, we're not using sine, we're not starting with sine, we're starting, hey, I have the opposite and the hypotenuse. So I know that sine of 30 degrees has to be the opposite divided by the hypotenuse. Okay, so I get this nice equation over here, right? So sine of 30 degrees is 8 divided by this H value. Okay, now I could solve this for H. I'm going to multiply on both sides, right? I'm going to multiply both sides of this thing by H, okay? And so on the right-hand side, they end up canceling out. And so we're left with this. We're left with, we're left with H times sine of 30 degrees is 8. And so if we keep going here, we would get that our value H is equal to 8 divided by sine of 30 degrees, right? So whatever that number is. So does anybody remember what sine of 30 degrees is? If we don't, we could look it up. We could use Desmos, right? Right, so that would be, I feel pretty confident that everybody can put this into Desmos. Another thing that we could do, right? So if this is me, I don't know if it's me being lazy or
Is it
whatever.
1/2? Sorry, I might have interrupted you.
No, go ahead.
Is it 1/2?
Is it 1/2?
Sine of 30?
I don't remember, honestly. I'm gonna tell you here in a second, right? So remember this table, sine of theta, cosine of theta. Good. This thing was 0, pi over 6, pi over 4, pi over 3. So give us some more space here. Pi over 3, pi over 2. Does everybody remember this table that I'm making here? All right, so if I fill this out, right, I know that sine of 0 is 0, so this is 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1, and then if we go backwards. Right, and so our angle measures up here at the top are, if we want to think about these in degrees, this would be 0 degrees, 30 degrees, 45 degrees, be 60 degrees and 90 degrees. Okay, so if we look it up in our table, are you right? So sine of 30 degrees looks like it's 1/2, right? So this should say we have 8 divided by 1/2, which is the same as 8 times 2, which is 16. Okay. So Jordan, you're right. Yeah, it's 1/2. Right. So going back to my triangle over here, we have lots of information so far, but let's go ahead and keep filling this in. Right. So this side should be 16. And are we done here?
No.
No, I mean, so there's lots of paths forward though at this point, right? So if you want to, you could use Pythagorean theorem. You could use cosine if you wanted to, and do something similar. Generally, what I find is students want to use the Pythagorean theorem. Is that true here for you all too? Do you prefer that when you can?
Yeah.
Right. So we'll go ahead and call this x. So what we would get is we get x squared, right, plus 8 squared is equal to 16 squared. And so if I multiply all this out, we would get x squared is equal to, let's see, 16 squared is 256. So this is 256 minus 64. Okay. So what we get is x squared is equal to 192. And so x, this bottom side length, would be the square root of 192. Okay, and so putting this all together, we could get this down here, 192 square root. Okay. So how do we feel about that, right? So all of this put together, right? So we would get all these things. These are our side lengths. We were able to now complete our journey, right? So the whole picture is right here. And then sort of remember at the beginning of this, we were tasked with figuring out all the information on this one triangle, right? So we have these side lengths, and we're going to figure out, hey, what, we started with just this information, right? So we determined this green, we determined the red and the blue, right? The only things that were given to us were the 30 degrees, this 8, and then a right triangle, right? So with 3 pieces of information, we were able to go around and sort of, it's like solving a puzzle, right? So we did all this work, and then we were able to, solve the puzzle and figure out the rest of the triangle. Okay, so any questions about this so far?
I'm all good. Seems understandable.
Pretty good. All right.
Yeah, that makes sense.
So we've got 2 minutes. I'm not gonna go through a whole nother one, but the other one in our notes was this triangle example right here. So if we just talk through it really quickly, what is sort of the difference? What is the difference between this example and the one that I just went through?
Since the angle is on the top side, would the 5 be the opposite?
That's exactly right. Yeah. So the one big thing that I want to point out, right? This would be our opposite side, and this would be our adjacent side. And so this would still be our hypotenuse, right? So that's a good pickup right there, right? So you'd have this opposite, adjacent, hypotenuse. And then when you use 15, do we have a nice way to look this up in a table? Like, do we have is this one of our sort of common angles that we see? It's not, right? So it's not 30, 45, 60, or 90. So this is one where we probably want to rely more on the calculator. Okay. So I won't go through this one here, but I'll leave this for Thursday, right? So if you want to think about this, this is the first one that we'll do on Thursday. And then we'll continue to think about these ideas of, how do we put all this together? And then on Thursday, we'll do section 7.2, where we're given some other pieces of information. We're actually going to be given none of the angles. We're going to use the inverse trigonometric functions to determine what the angles are. Okay, so we'll see this on Thursday, and then we'll see some modeling problems as well. So don't know if you hear in the background, but my daughter knows it's time. It's 11. So, any last questions before we go here?
No, I'm all good. Thank
Nope.
you.
Good. All right. Well, I hope you're all well. Stay safe, healthy. I hope things are going well. Anything that you need, let me know. I'll try to do what I can to help. But I hope to see you all on Thursday. See you then.
All right. Thank you.
You're welcome.
Bye-bye.
Bye.
Bye.